All right, I guess we'll get started. Have you guys seen this announcement already? Anybody? Okay, so we were asked to make this announcement. I can't do anything about the radiator, sorry. That's really annoying. Humam Saknini, he's a Queen's alumnus. He's now president of, or has been president of King Games. They're the people who make Candy Crush and a bunch of other, wow, that radiator is really annoying. He's that's the company that makes Candy Crush and a bunch of other social media games. I think they're the biggest, well, Tencent's probably the biggest mobile game maker. They're probably the second biggest mobile game maker. He's giving a talk next Thursday. If you're interested in listening to his talk, which I assume he's going to be talking about the game industry, you just have to register for the talk at the link there. And I think that's so that you can get into the talk automatically, because it's going to be on Teams or Zoom or something like that. Yeah, so you can listen to what he has to say. All right, we were talking about conversion of types in C. So there's a bunch of integer types in C. Anything shown in red here, so basically anything that's short or smaller is called a small type. Now the strange thing in C, and this is also true in Java, is that if you try to do arithmetic with a small type, then that type gets the value of the type gets converted to int. The arithmetic gets done using int, and then the value gets converted back to the small type. And so in this example here that you saw last day, it's using signed car for the type. Now the largest value of signed car is 127 on my computer. Right? So if I add two signed car values, 150, right, that would normally overflow if C didn't promote the type to int. Right? So the largest value is 127. If you add 150, that's bigger than 127. You would expect overflow to happen. It doesn't happen with the small types. So instead, that sum, C1, C2, that gets computed using int, and int can comfortably hold the value 150. So no overflow occurs. 150 gets divided by 2, you get 75. That easily fits inside the range of signed car, and so you end up with the correct result. Right. Now, when you have mixed types that aren't necessarily the small types, the rules get a lot more complicated. So when you take into account the floating point types and the integer types, what ends up happening is the four rules here get applied. Right? So in order, right, one of four different things happens. Right? If one of the operands has type long double, something happens. Right? Now long double is the largest standard floating point type in C. But if that's not true, it's probably not true in this course, because you're probably never going to use long double in this course. So rule number 2, if one of the operands has type double, then something happens. If one of the operands has type float, then something else happens. Right? And then finally, if both operands have some integer type, not necessarily the same, something else happens. Right? Okay, cases 1, 2, and 3. So if one of the types has type long double, then both operands are, then the other operand is converted to type long double. So all this is saying is that the smaller type gets converted to the wider type. So if one of the types is not long double, but one of the types is double, then the other operand gets converted to double. Right? And then finally, if one of the types is float and the other type is the other type is an integer type, then that integer value gets converted to float, which is strange, because that means long, which is normally 64 bits on most desktop computers, will get converted to float, which is only 32 bits. Right? And so that means your long value probably can lose precision when being converted to float. But that's the way it works. Right? So there's a slide that you probably can't read, so I'm just going to show you the source code directly. Oop, I don't want that. So this is here. Okay, so we've got a little C program here. This is case number 1 up here. right? So in case number one of my operands, I'm going to add x and y here, right? So one of my operands, in this case x, it has type long double. Right? My other operand, it doesn't matter what the type of the other operand is, right? It happens to be double here. I'm going to convert, so when I do the sum, the value of the y will be converted to a long double as well. All right, now notice that y is set as double max, right? So that's the largest possible double value, right? If I compute the sum, x plus y, right? X has type long double, so the value of y also gets converted to long double, and then the sum gets computed. Right? So that sum will be twice times double max. At least it should be anyway. Right? And then we can print it out. I'm going to print it out in a couple of different ways. Right? So minus L, that will convert, sorry, let's look at the E first. So the E will use exponential notation. Right? So I'll show you what that looks like in a second if you're not familiar with it. The L indicates that we're using long exponential notation, right? So that's what you need to use if you want to print out a long double value. You either use LE or LF. Right. Let's take a look at what happens when you run that program. So this is F mixed types, F mixed like that. So we just want to look at the first two numbers here. Right. So double max apparently is 1.8 times 10 to the 308, right? That's some ginormous number, right? The sum should be twice that, and it is, right? So the sum's computed correctly. You can do the same thing with float. Where's double? Hang on, sorry. I just want to see, okay, that's there. This is case, what does the slide say? Oh, sorry. There we go. Oh, right. Sorry, I was explaining. Okay, exponential notation. So exponential notation prints things out with an E, right? So in exponential notation, that number there is always has one. Sorry, one. Yeah, it's always one digit in front of the decimal place, followed by some number of digits after the decimal place, times 10 to the power 308, right? So that's how exponential notation works, or scientific notation works. Sorry, right? So always that number there. There's always one digit here, right? Never more than one. And I think it's always bigger than 0. I think it's never 0. Okay, next example, we're going to use, what's y? So y is a double, right? And I'm going to set the value of y to float max. So that's the largest float value that you can represent, right? And then z is going to be a float, also equal to float max. And then I'm going to compute the sum of y and z, right? So y has type double, z has type float. The value of z gets converted to double. The sum gets converted as double, gets computed as double. Right? And then the sum, what's the sum stored in? And the sum has type long double. Right. So print the result out. Looks like I'm going to print float max. Oops, sorry. Come on. Right, so you see that float max is 3.4 times 10 to the 38. And the sum, it should be twice float max, which it is. Right, so we're not seeing any sort of overflow errors happening here. And then finally, the last example. Okay, so in the last example, this corresponds to case 3. Right? One of your operands is a float. Right? So in this case, z is going to be a float value. Right? So in this case, it's the largest short value. I'm going to add it to I'm going to add a second value to z that's also of type short. Right? So the sum z plus s, right? That short value s gets converted to float, and then the sum gets computed using float arithmetic. Oh, wrong slide again. Come on. Whoa. There. Okay. So that's the largest short value. Right? 2 times that value computed using float is that value there, which looks correct. And this is probably all screwed up now. Right, so that's what happens when you have a mixed type conversion. Right? Basically, the rule is you convert the narrower type to the wider type. Right? The thing you have to remember is that all the integer types are skinny or narrower than all the floating point types, right? Which is weird. So rule number 3 is strange, right? If you have an integer type and you add it to float, it gets converted. The integer type gets converted to float, even though some of the integer types are actually can hold a wider range of values than float does. Okay, moving right along. Case 4. If both operands have integer type, then integer promotion is applied if required. Right? So in other words, if one of your values happens to be one of the short types, that type gets promoted to int. Right? Now, after that happens, you've got 2 integer values that you're doing something with. Right? So after the promotion occurs, you now convert according to the following set of rules. The problem with the integer conversions is you have the unsigned types to consider, right? Which complicates things. Okay, so now there's 5 separate cases, right? So you're adding 2 int values. You've done the promotion if one of them happens to be a short value. And now you have to consider how is the calculation performed. So if x and y have the same type, nothing happens. Right? If x and y are both signed, or if they're both unsigned, something happens. Right? Now you have to consider what happens if one of your values is unsigned and the other one happens to be signed. Right? So if the unsigned operand has rank greater than or equal to the signed operand, something happens. Right? Case 4, the signed operand can represent all the values of the unsigned operand, something else happens. And then 5 is the catch-all case. Right? So then if none of the first 4 are true, then the 5th case happens. All right, so case 1, x and y have the same type, nothing else happens. Right? So if x and y both have type int, it just uses int arithmetic. Right? If they both have type long, it uses long arithmetic. If they're both unsigned int, then it just uses unsigned int arithmetic. Okay, if they're both of the signed type or they're both unsigned type, right? So you have an int and a short, a long and an int, or you have an unsigned long and an unsigned int, right? Then the operand with lower rank gets promoted up to the higher one, right? So int and long, the int gets converted to long. Unsigned int, unsigned long, the unsigned int gets promoted up to unsigned long. The real problem happens when you run into case 3. Right? So you have an unsigned operand and you've got a signed operand. Right? If the unsigned operand has rank greater than or equal to the signed operand, right, then the signed operand gets converted to the type of the unsigned operand. Right? That's a problem because if the signed operand is negative, the result you get is probably not the one you're hoping for. Right? So we'll look at an example of that in a moment. Right? Actually, why don't we look at that now? So under mixed types. Okay, so this is case 3. So it's this case here. So I've got an unsigned int value called z. Right? So it's unsigned int. I'm going to add 1 to z. Right? So 1 has type int. Right? So what does case 3 say? Case 3 says if the unsigned operand has rank greater than or equal to the signed operand, then the signed operand is converted to the type of the unsigned operand. Right? So does unsigned int have the same rank as int? The answer is yes. So that 1 gets converted to an unsigned int. Right? And then the sum's computed using unsigned int. Right? So we can print out the result here. So let's see what happens when we run this example. So this is, oops, sorry. Okay, so this is, let's just find out what we're looking at here. So we're looking at int max and sum. Oh, actually, how many? We're looking at the second time int max and sum gets printed out. So here. Right, so we start out with int max. Right, so that turns out it's 2147, ends in a 7. Right? The sum is 1 bigger than int max, which is good, right? So because the sum is computed using unsigned int. Right? Now remember, unsigned int, its upper bound is higher than int. Right? So it turns out you can actually add 1 to int max and get the right answer. Right? If you store the result, if you compute the result using unsigned int. Right? So that's good. That seems to work. Right? We'll look at the surprising case in a few minutes, I think. All right, now if the signed operand can represent all the values of the unsigned operand, then the unsigned operand is converted to the type of the signed operand. Right? So an example of that would be if your signed operand has type long, your unsigned operand has type unsigned int. Right? Now the unsigned int gets converted up to long. Right? So that occurs when the signed type is wider than the unsigned type. Right? So if your signed type is long, then any unsigned int gets converted up. If your signed type is long, then an unsigned long will get converted up to long. And case 5 is your catch-all case. So that occurs when your two types are represented with the same, two different types are represented with the same number of bits, and the signed operand has greater rank than the unsigned operand, right? Which is unusual. Okay. So what happens here is both operands are converted to the unsigned type. Both operands are converted to the unsigned type. To the unsigned type of the operand having the signed. Oh, both operands are converted to the unsigned type of the operand having the signed type. And this one's also weird. So where is case? Hopefully there's a case 5. Okay, so there's case 5 is this slide here. And so let's see what happens in that example if I change that 1 to a -1. All right, so this is the case. This is case 3. So let's go back and look at what case 3 is quickly. Case 3, unsigned operand has rank greater than or equal to the signed operand. Wait, so unsigned operand is unsigned int, right? -1's an int, so they have the same rank, right? So we're going to take the signed value, convert that to an unsigned value. Right? So we're going to take that -1, convert it to a signed value, and then compute the sum, right? So let's see what happens when we recompile and run that. GCC. Oh wait, that's not right. Sorry, mixed. Okay, so that seems to work okay, right? So remember I took this value here, right, and added -1 to it, right? So if you subtract 1 from that value, you get that value there, which looks okay. Right? So what if you put in, what if you put in a different value here? Right, so here I'm going to use something like that. Recompile. Whoops, sorry, recompile. Run it again. Right, you look at the answer, still seems to work. Right, so it still seems okay. Add a few more zeros. And it still seems, oh, let's see what happens. And it still seems okay, right? So it still seems like it's working. Right? But if you play around with the values that you're plugging in and you compute the sum, right, with case 3, you're going to find out that sometimes you're going to get a very strange result. The reason you get the strange result is because of the way that the numbers are represented when you use 2's complement, right? So when you use 2's complement, remember the signed values are all 2's complement. The unsigned values are just plain old binary numbers, right? So when you convert a negative signed value, right, back to its, when you convert a negative signed value to its unsigned counterpart, you end up with a weird result, right? Because that first, the most significant bit of the unsigned number is a 1, right? But that's the most significant bit of the unsigned number as well. So play around with that example and see if you can't get it to barf, right? It's not that hard to do, right? You can easily get it to produce a result that's very weird. And the same thing happens with case 5, right? Whenever you're converting an unsigned value to a signed value to an unsigned value, right? That first or the most significant bit of the signed number is always a 1, right? But that's the most significant bit of the unsigned number, which is strange, right? So give it a try, see if you can't get it to mess up. I think here's a case where it actually does mess up. So here you've got an unsigned int, right? And its value is the largest unsigned int value, right? I then have a signed car value, right? Now remember, signed car, that's small. So this thing here actually gets promoted up to an int, right? And then the comparison happens here, right? So look, I've got the signed car minus 1. I'm comparing it to the largest unsigned int value, right? So I'm going to check, are they equal, right? If they're equal, something's going to get printed out, right? But why won't you give me my terminal? There we go. Right? So apparently minus 1 is equal to 429,496,7295. And there's the code right there. Right? So minus 1 is equal to the largest unsigned int value, right? Which is strange, right? It's bizarre. So why does that happen? Right? So why does that happen? So what's your largest unsigned int value? Right? Your largest unsigned int value in binary, right, is 1, right? 1, 1, right? It's all 1s because it's unsigned int. So you have 32 of these, probably 32 of these, right? That's your largest unsigned value, right? Now, that signed value, it's a signed car, right? It's only got 8 bits. Right? It's only got, which is weird. It's only got 8 bits, right? But it's converted to an int. So it gets converted to unsigned int, right? The minus 1 as unsigned int, right? Because that's the type of UI, right? Now, what's minus 1 as an unsigned, what's minus 1 as an int value, right? So that signed car, it's one of the short types. It gets converted to int. So it gets converted to minus 1 as an int, right? Remember now, it's a signed value, so it's using 2's complement, right? So that first digit has to be a 1, right? And if you go back to the previous slide, hopefully I have them up. I probably don't have them up. It is worth letting me go back to look at the previous slide, though. Where is, here. So the value of minus 1, right, when you're using the 2's complement representation, right, is all ones. So minus 1 is equal to that. This is whatever that big number was, right? So in 2's complement, minus 1 has the same bit pattern as that, right? That's the unsigned number, right? That's an unsigned int. That's the signed int equal to minus 1. They have the same pattern, right? The same bit pattern. Right? So when you do this comparison, right, and you apply the rules, right? Step 1, that gets converted to signed int, right? So that minus 1 as signed car gets converted to that, right? Now you have a signed int and an unsigned int, right? So now the comparison happens using unsigned int, right? But all the comparison does is look at the bits, right? The bits are the same, right? So apparently, as far as C is concerned, the number minus 1 is equal to whatever that value is there, which is that, right? And this is all a byproduct of the fact that of the rules that are used to convert between these signed and unsigned types, right? So it's very strange. If you're working with the unsigned types and you're trying to do arithmetic with a signed value, you have to be very careful when you add the signed value, or when you take the signed value and do something with an unsigned value to it, right? And it's because of that bit that's sitting out here, right? If the number is negative, that bit's 1, right? The most significant bit's 1. But that's the most significant bit in the binary, in the unsigned number. Okay, safe conversions. Right? So that was an example of an unsafe conversion, right? Minus 1 should not be equal to 4 billion, whatever that was, right? That's some huge number. So when are you guaranteed that the conversion happens safely, right? So if your signed integer has a smaller type, right, then you can always convert it safely to a signed integer of a larger type, right? I can always convert int to long without any issues. Right? An unsigned integer of a smaller type can be safely converted to an unsigned integer of a larger type. Right? So I can convert unsigned int to unsigned long without any issues. Float you can always safely convert to double, right? And you can always safely convert it to long double. Right? And double can only ever be safely converted to long double. Right? All of the other conversions are potentially unsafe. The rules are different for bool. Oh, except for bool. Okay, so floating point to integer. So if you have a floating point value and you want to convert it to an integer value, what happens? Right? So the floating point value is converted to an integer type. The way it works is you throw away everything after the decimal place. Right? So 1.5, if you convert it to an int, just gets 1. Right? You throw away everything after. There's no rounding. No rounding occurs. Now, after you throw away the decimal part of the number, right, you're left with the whole number part of the floating point value, right? If the whole number part cannot be represented by the integer type, then the conversion is undefined, right? So in other words, the compiler is allowed to do whatever it wants. So here's an example of converting a float to an int. Right, I've got the float value 1.5. Right, I'm going to store x in y. Right, so I want to store the value 1.5 in this int value y. Right, so the way it works is throw away the 0.5 and store the whole number part. Right, does 1 fit safely into int? Yes, the answer is yes. Right, now what happens if you convert float max to a int value? Right, so float max is much bigger than what you can store in an int, right? So float max is something times 10 to the 38, right, which is much, much bigger than the range of int. So let's see what happens on, sorry, I just have to find the file that this corresponds to. It's none of these. Where is the, oh, here. Float, so I'm looking, oh, float to int, okay. Float to int. Okay, so when I convert 1.5 to an int, you get 1. So that's all right? You throw away everything after the decimal, right? When I convert float max, which is some number times 10 to the 38, when I convert it to an int, you get that. That happens to be the equivalent of integer min value, so the most negative integer value, right? Which is weird, right? So float max is some large positive value. When you convert it to an int, right, it gets converted to some large negative value, at least on my computer. On your computer, you might get something different, right? Especially if you're using a different compiler. The other thing to notice is that the compiler doesn't help you in this case. So if you compile that program, right, the compiler doesn't warn you that this is happening, right? You get no error diagnostic whatsoever, right? C simply does the conversion, right? So that conversion there, even though it's unsafe, right, it happens automatically. This doesn't happen in Java, right? So if you try to do this conversion in Java, the compiler will stop you. It'll say this is unsafe. You can't do this without a cast, right? So Java tries to prevent you from making any mistakes. C has the opposite. C takes the opposite approach. C assumes that the programmer knows what they're doing and simply does what the programmer tells it to do, right? So C assumes that you know how this conversion works and simply applies the conversion. Right? So you get no warning that this is happening, right? All that ends up happening, well, whatever you told it to do, it tries to do, right? That conversion there is undefined, right? In this case, you happen to get the largest negative integer value. The most negative integer value, right? But you could get something else. If the value of the integer part fits in the range of the floating, so this is when you go from integer to floating point. Right? So if the value of an integer fits into the range of a floating point type, then the integer value is converted to the closest possible floating point type. Right? You have to be careful with this. So I have a float. Sorry, I have an integer value. I want to convert it to a floating point value. Right? Now float and int, they both occupy 32 bits. Right? But float represents a much wider range of value than int does. Right? So what does that mean? That means there's some int values that you cannot represent exactly in float. Right? So if you convert an int value to a float value, there's no guarantee that your floating point value is exactly the same as the original integer value. Right? Similarly, long and double both occupy 64 bits. Right? But there are long values that cannot be represented exactly using double. So when you convert your long to a double value, there's no guarantee that the corresponding double value is exactly equal to the original long value. Right. If your integer does not fit into the range, then the result is undefined. Right. Can that actually happen? If the integer doesn't fit in the range, when would that actually happen? I don't know when that would actually happen. I don't think you can actually do that. I guess if you tried to convert a long to a float, that might be a problem. But normally it's not an issue, because float, its maximum value is 10 to the 38, which is bigger than long. Which is bigger than the largest long value. Right? So there's a potential loss of precision when you go from an integer to a float. Is there an example here? Okay, so here I'm going to convert x, which is 101. I'm going to convert it to a float. That should happen without any issues, because you should be able to represent 101 as a float. If I take an int max and try to convert that to a float, let's see what happens there. So this is, back here, int to float. Okay, that's good. So if I convert the integer value 101 to the float value, you get 101.000000. So that looks like the conversion happened correctly. Right? In other words, the value of y is equal to the value of x. If I convert that value of x to float, right, the answer is not the same. Right? So notice you get 547 here, and at the end here you get 520. Right? So in other words, that int value does not have an exact corresponding float value. Right? There's a loss of precision that happens. Right? The same thing will happen if you try to convert a long to a double. Right? If you try to convert a very large long value to a double value, you'll lose some digits of precision. Oh, and finally, floating point to floating point conversion. So this is if you try to convert a double to a float or a float to a double. So if the value of the floating point value, if the value of the floating fits in the range of the chart. Okay, so if the value of the floating point value that you're trying to convert fits into the range of the type that you're converting to, then the value gets converted to the closest possible floating point value. Right? Otherwise, the behavior is undefined. So if you try to take a very large double value and convert it to a float value, that's when you get undefined behavior. Right? Whenever you see behavior is undefined in C, that should scare you, because anything can happen. Right? Usually what happens is the program does not crash, which should terrify you, because you have no indication that something's gone wrong. Right? So whenever you see something has undefined behavior, all sorts of warning bells should go off. Right? Try to avoid doing something that has undefined behavior. So here's an example. I'm going to convert 100.5 to float. That should work seamless. That should work without any issues. Right? 100.5 is not that big. Right? So if I convert it to float, that should be fine. If instead I use float max times 2, so that's 2 times the largest floating point value. If I try to convert that to a float, we should expect something weird to happen. And so this is double the float. So convert 100.5 as a double to 100.5 as a float. That seems to work just fine. There's the largest, that's float, 2 times float max, right? Written out with all of its digits and all of its glory, right? So that's 2 times float max. If you try to convert that to a float, you end up with positive infinity, right? At least on my computer with my compiler, right? If you try to do it with something on another computer with a different compiler, you could get a different result, right? Because the standard says behavior is undefined, right? So you may or may not get positive infinity in that case. All right, so the type conversions, the rules are complicated, right? But you need to be aware of them in the event that something strange happens. Now, am I going to ask you about the type conversion on an exam? The answer is no, right? So don't be concerned that I'm going to ask you about rule number 5 under the conversion, right? It's never going to happen, right? I don't think it's not useful to ask you that on an exam or a test, right? But you have to be aware that these conversions are happening, and you need to know how if you program in C for your as your career, you need to be aware of how the conversions actually work. Okay, type qualifiers. So far we've been just working with plain old types. But in C, you're allowed to change you're allowed to apply what are called qualifiers to the types to change the meaning of the type. Right? Now there's there's 4 different type qualifiers that you can use in C. Right? We only care about the first one in this course. Right? The other ones are important, but they're not relevant to this course. Okay? So the one I'm really concerned about is const. So if you declare an object with the const qualifier, then the object itself is not modifiable. Right? So you cannot assign a value to, you can't assign a value to a const variable. Right? You can initialize it, right? So you can give it an initial value. Once you've given it a value, you can't reassign to it. Right? the compiler is allowed to place a const qualified object in read-only memory, right? So in other words, if the compiler decides that it wants to allocate memory where things are permanent, right, read-only, then it's allowed to put anything that's const in that memory, right? That memory might be faster, it might be easier to access, something like that, right? But that's what the standard says the compiler is allowed to do. So if I make a variable called I, whose type is int, right, and I say that it's const, right, then this is effectively saying that I always has the value 1, right? If you try to write I equals 2 on the next line, right, that's when the compiler will tell you that you're not allowed to do that, right? So this will result in a compilation error, right, because I has been declared to be I is declared to be const. Right? So we can actually try that. So const C, and so there you go. Right, so if you try to compile that program, you see you get an error, assignment of a read-only variable. Right? In other words, I is const, you can't change its value. All right, so making a constant value, it's pretty straightforward. It's obvious what it means. The problem is when you have a pointer, right? So can I create a pointer to a const qualified object? The answer is yes, right? A modern compiler will warn you that the const qualifier is lost if you do so, right? And the result is undefined behavior if you modify the object via the pointer. So what does this mean? Right? So there's the exact same slide as before, right? So I make my variable I mark it const. Right? So in other words, I always refers to this value 1. Right? But I can take a pointer, right? So I can make a pointer to an int, right? And I can point it at that value that's stored in I. Right? So remember what this does, right? So P, star P means that P is a pointer. Right? It's a pointer to an int object. Right? The and means the address of I. Right? So P points to whatever I is. Right? So in other words, P is pointing to wherever 1 is stored in memory. Right? That's what it means. Now, star P. So what does that mean? That means dereference the value of P. Right? So in other words, give me the object that P is pointing to and change its value to 2. Right? So in other words, it's going to try to change that 1. Right? Remember, in memory, that value is 1. I'm going to go into memory. I'm going to try to replace that with 2. Right? But I was marked const. Right? So you would really like for this not to work. Right? Unfortunately, in C, it does. Right? Well, it could do something. Right? So if you print out the result, right, you would like to see 1, but I'm pretty sure on my computer you get 2. So this is, const 2. In fact, it does change to 2. Right? If you compile the program, const 2C. Okay, you get a warning. Right? So in the function main, you get a warning on line 7, right? Column 14, right? Initialization discards the const qualifier from the pointer target type. Right? So it's right there. Right? So when you take your pointer and you say, I'm going to point it to whatever is sitting in I, right? That lets you go in and actually change the value of I, even though I was declared to be const. Right? So even though I was declared const, you're still allowed to take a pointer to it. Right? Using the pointer, you can go in and change the value. Right? Does it work? It seems to work on my computer. Right? Is it guaranteed to work? The answer is no. Right? The runtime behavior is undefined. It happens to work on my computer with my compiler settings. It may not work on your computer with your compiler settings. Okay, now what happens if you want to make a pointer to a const qualified object? Right? So that thing I is const. I really shouldn't make a pointer that's also where I can change the value of I using the pointer. Right? So if I want to make a pointer to a const qualified object, you should declare the pointer to be also const. Right? And now the compiler will prevent you from trying to change the object pointed to. right? So for example, in that example, if I write const int star p, right, that declares a pointer to a constant int object. Right? Now the way you read this is, right, so there's this, oops, sorry, there's this, it's going to skip. Where is it? There. So star p means that, so the star means that you've got a pointer, right? What is the pointer pointing to? It's pointing to a const int object, right? So pointing to a const int object, right? So that means when you use the pointer p and you try to change, right? So I use p and I make p point at I and I try to dereference p and change its value. Now the compiler will tell you, now the compiler will prevent you from doing this, right? Because here you're saying p points to a constant int object. If you try to dereference the pointer and change its value, the compiler will flag that as an error. So this is probably const 3, I'm guessing. Const 3. There you go, right? So there's your error, right? Assignment of a read-only location. All right, so if you have something declared const and you want to take a pointer to it, make the, also declare the pointer in a way such that the compiler can figure out it's also pointing to a const object. All right, so I'm going to stop. I think there's only a couple. Okay, let me just finish off the const slides. All right, so that's a pointer to a const object. What if you want the pointer to be constant? Right? So in other words, what happens if you don't want someone to be able to make the pointer point to something else? Right? So now the syntax changes a little bit. Right? So if you want the pointer to be constant, right? So in other words, I want the pointer to always point to the same object, then you use the following syntax. Right? So now the const appears after the pointer type. Right? So here int star says that p is a pointer, right? The const says that it's a constant pointer, right? So notice the difference here, right? So here, const int star p is pointing to an object that's constant, but you can change p, right? So I can make p point to something else, right? Here, int star const p means that p is a pointer, p is a constant pointer to an integer object, to an int object, sorry. Right? So what that means is when you assign it some value, you can't change what it points to after that. Right? So that declares a constant pointer to an int object. So here's an example here. Right? So const int I equals 1. Right? So in other words, I is a constant value. Right? If I try to make a pointer, a constant pointer to that value, you get a compiler warning. Right? Why do you get a compiler warning? Because in this example here, p, the pointer p is constant, but the thing it's pointing to is not. Right? So this is saying p is a constant pointer, but it points to some int. Right? You really want to say it points to some constant, because that's what I is. So you get a warning here, and then you get an error here. Right? You get the error here because you're trying to change a constant pointer. Right? Pointer p is constant here, you give it a value, right? I can't give it another value now because the pointer itself is constant, right? So even if I try to reassign it back to I, it still doesn't work, right? So if you try to compile this thing here, right? So there's your warning, right? So it's telling you that you're creating a pointer to a const object, right? But you didn't say that the object was const, right? And then you get an error, right? Because the pointer here is constant, it's assigned a value, and then you try to give it another value here. Right? Is the fourth example? There's one more. Okay. So the last slide. If you want the pointer to be constant and the object pointed to be constant, then you have to combine. And then you need two consts, right? So const int star const p. Right? How do you read this? Right? P is a const pointer to a const int value. Right? So in other words, you're sort of reading it from right to left. Right? And so in this case here, is there an example? No, there's no example here, right? So here, I can't change p, right? And I can't change whatever some int is either. Right? If you try to do either of those things, the compiler will flag that as an error. Right? So that's const as it applies to regular variables and to pointer type variables. Any questions? You have to play around with it and try out some examples in order to absorb it properly. Right? So I encourage you to try some examples. So grab the source. So just type in the programs here and try monkeying around with it. So try to change the value of p or try to change the value of I using the pointer p. See what works and see what doesn't. Right? It's the only way that you'll actually understand what's happening. Okay? Your midterms are, half the midterms are marked. The rest of them should be marked this afternoon. So I'm going to try very hard to get the rest marked before 5 o'clock today. But the first half of them are marked. So far, people are doing reasonably well on them.